students, let us discuss determinants from standard 12. In this video, I shall explain how to expand a determinant and evaluate it. I shall also explain the properties of determinant and solve a few questions based on the properties. So watch the video till the end to have a better concept of the chapter. Let us begin with the definition of determinants first. So a determinant is the arrangement of elements in rows and columns within a symbol which looks just like a pair of parallel lines. So if I talk of determinant A, then symbolically it will look like this. Now as I said, it is the arrangement of elements in rows and columns. So just like in matrices we have rows and columns, here also we will have rows and columns. Let me begin with a second order determinant first. So here A, B, X, Y. So you can see we have two rows horizontally and two rows vertically. So this is a determinant of order 2, a second order determinant. So this is the first row with elements A, B, right? This is the second row with elements X, Y. And the first column, that is vertically, we have A, X. This is column 1 and this is column 2. Fine. Now if I talk of a third order determinant, then there will be 3 rows and 3 columns. So first row elements, I am writing here 1, 2, 3. Second row elements 4, 5, 6. Third row elements 7, 8, 9. So this is the first row with elements 1, 2, 3. There are 3 rows here. Row 1, this is row 2 and this is row 3. Vertically, the elements are 1, 4, 7. This is column 1. Then 2, 5, 8. This is column 2. 3, 6, 9. This is column 3. So here there are 3 rows and 3 columns. So this is a determinant of order 3. Now, before we learn how to evaluate a determinant, we must learn about the terms cofactor and minors. So what are, first of all, minors? Minors are again elements which are obtained by replacing the row or column in which an element of the determinant occurs. Now as I said, 1, 2, 3 for the previous determinant, 4, 5, 6, 7, 8, 9. So as there are 9 elements here, each of the 9 elements will have their own minors, right? And how is the minor obtained? By omitting the row and column in which the element occurs. If I talk of the first element 1, you can see 1 occurs in the first column. I will eliminate that. 1 also occurs in the first row. So I will have to eliminate the first row also. Then I am left with 5, 6, 8 and 9. So 5, 6, 8 and 9. This is a second order determinant which is the minor of the element 1. Similarly, minor of the element 2 now. 2 occurs in the first row. So we have to eliminate the first row. 2 also occurs in the second column. So we have to eliminate the second column. The left out elements are 4, 6, 7, 9. This is again a second order determinant here. So you can see for finding out the minors of the elements of a third order determinant, we obtain second order determinants, right? Now if I talk of the element 8, this element 8 occurs in the third row and second column. So if we omit the third row and the second column, we are left with 1, 3, 4 and 6. I am not changing the order of the elements. Please see. So here the minor of the element 8, you can see, is a second order determinant again. So now the value of these second order determinants can be obtained by simply cross multiplying the elements and then subtracting them. So for this one, it is 5 into 9, 45, minus 8 into 6 is 48. That is minus 3. Similarly, here also 4 into 9, 36, 7 into 6, 42. That is minus 6. In this case, 1 into 6 is 6, right? And minus 4 into 3 is 12. So, minus 6 here also. Next comes the term cofactors. Now, what are cofactors? Cofactors are same as minors but with an appropriate positive or negative sign in front of them. Now, they will also be second order determinants just like we found in the previous case. Now, look at the element 1. Its minor is 5, 6, 8, 9. Now, we always begin with a plus sign for the first element and then alternately we should consider the negative signs to find the cofactor of each of the elements. So here I am giving the appropriate signs required for the cofactors. In case of plus sign, we may not indicate with a plus sign, but for a minus sign, it is necessary to indicate using the sign of minus. So the cofactor of 1 is same as the minor of 1, right? Next, cofactor of 2. You can see I have written a minus sign here. So the minor should have a negative sign in front of it to become the cofactor. This is now the cofactor of 2, right? Next, I had written this as a minor of 8. Remember? Yes? Now look at the sign 8 has. 8 has a negative sign. So as this minor is given a negative sign now, this becomes the cofactor of 8. I hope you are clear with the terms minor and cofactors. As we have 9 minors for the 9 elements, we have 9 cofactors for all the 9 elements here. We only have to keep in mind the positive sign and the negative sign depending on the position of the elements whose cofactor we are finding out. Now, in order to evaluate a third order determinant, we will need the help of the cofactors. So, let me explain here again. I am considering a third order determinant with the same elements 1, 2, 3, 4, 5, 6, 7, 8, 9. So when I expand a determinant, I have to expand it with respect to any one particular row or any one column, right? Now I am willing to expand it with respect to the first row. So if I expand with respect to the first row, each of these elements will be multiplied by their cofactors and then added. So 1 multiplied with its cofactor. Cofactor of 1, you know, I have to eliminate the first row and the first column. I will be left with the second order determinant 5, 6, 8, 9. Next comes the element 2. So I am adding the next term now. 2 multiplied with its cofactor. Now the position of 2 says that its cofactor should have a negative sign. So eliminating the first row and the second column, we have 4, 6, 7, 9, right? Then the last element in the first row is 3. We add 3 and multiply 3 with its cofactor, which is positive 4, 5, 7, 8. So expansion of the determinant with respect to row 1 is over. Now if we evaluate the second order determinants and multiply it with the corresponding elements, that is 1, 2 and 3, our work will be over. So now let us evaluate the second order determinants and multiply with the corresponding elements. So 1 into 45 minus 48 plus 2 into minus of 36 minus 42, we are cross multiplying, okay, this into this minus this into this, then plus 3 into 32 minus 35. So here we have minus 3, then plus into minus is minus 2, and within bracket we have minus 6, then plus 3 into minus 3. So minus 3 plus 12 minus 9, this finally gives us 0. So this is how we expand a third order determinant and evaluate it. Now some properties of determinants. Let us discuss some properties of determinants. The first property of determinant tells that the value of a determinant remains unaltered when all the rows and columns are interchanged. So here I am considering a determinant with 9 elements, that is a third order determinant, P, Q, R, X, Y, Z. Now if I interchange the rows and columns, the new determinant would look like this. The first row becomes the first column. So here I have replaced the first row and written it in the first column. Next, the second row becomes the second column, P, Q, R, then X, Y, Z. Now if I evaluate both these determinants, you will see the answer is the same. So we can use an equal sign for these two determinants. Next property says that when any two adjacent rows or columns of a determinant are interchanged. So again I am writing the same determinant here of third order, and now when I interchange any two adjacent rows or adjacent columns, the value of the determinant will remain same but the sign will change. So here when I interchange row 1 with row 2, so the new row 1 will have elements PQR, row 2 will have elements ABC. Third row remains unaltered. Now can I use an equal sign here? I can use an equal sign provided I put a minus sign here. So when any two adjacent rows are interchanged, you can see I can use the equal sign provided I give a minus sign. The same is the case when I interchange any two columns. So here if I interchange column 1 with column 2, then B, Q, Y comes here, A, P, X goes to the second column. Third column remains unaltered, right? So from this step, can I come to this step using equal sign? If I put an equal sign, I have to put a minus sign, because in this case column 1 and column 2 has been interchanged, whereas in this case row 1 and row 2 has been interchanged. So this was property 2. Next comes property 3. When any two rows or columns are identical, the value of the determinant becomes 0. So we have to keep in mind that when any two rows or any two columns are exactly the same, their order of the elements are also the same. So here row 1 and row 3 looks exactly the same. So the value of the determinant is directly 0 without expansion. We can write 0 here. Next, the fourth property says that when every element of a particular row is multiplied by a constant, right? So here you can see row 1 has a common factor m. It implies, means this is equal to the determinant is multiplied by the constant m. So A, B, C, X, Y, Z, P, Q, R. So we can think in another way, as if the factor m has come out common from the first row. If a determinant had another factor common, suppose here I had 2, 2, 2, right? So from column 2 the factor 2 can come out. and finally the constant that is multiplied with the determinant will be 2m. I hope the fourth property is clear. Next, the fifth property. Now the fifth property states that when the elements of a particular row are expressed as the sum of two terms, like here a plus x1, b plus y1, c plus z1. This is the first row, x, y, z. Second row, p, q, r. Third row. What do we observe here? We observe that the first row elements are expressed as the sum of two terms. So this single determinant can be splitted into two determinants by a plus sign in between. So I can use an equal sign here. Now how do I split the single determinant into two? It is like this. The first term of each of the elements from the first row will come to the first determinant. So ABC comes here, right? And the second term goes to the second determinant, x1, y1, z1. Now as both the terms had a plus sign in between, you can see we are having a plus sign here. And the remaining rows will remain the same in both the determinants. Okay. Now this is applicable only when we are splitting a single row. If all the elements of this determinant are expressed as the sum of two elements or two terms, we can never split up all the elements into two determinants. At a time, we shall only split up one particular row, and a single determinant will split up into two determinants in this way. So this is the fifth property. Next comes the sixth property. This is the most important of all. You will find several applications of it in the exercise. So the sixth property states that the value of a determinant remains unaltered if to all the elements of any row or column are added the same multiples of the corresponding elements of any other row or column. So here if I have a determinant in this way, A, B, C, X, Y, Z, P, Q, R. Now I wish to change the elements of row 1 as row 1 plus m times of row 2 elements plus n times of row 3 elements. So what happens now? Row 1 changes. You can write here R1 dash to indicate a new row. So row 1 elements means the first element A will be simplified with either X or P or both. It will not be simplified with YZ or QR, right? So row 1 plus m times of row 2 plus n times of row 3. So this is the first element here, and now we need a wider space. So I'll put the last symbol later. Next comes the next element, that is B added with a multiple of Y and then added with a multiple of Q. So B plus MY plus NQ. Next C with Z and R. So C plus MZ plus NR. So the first row elements have changed in this way. The remaining rows remains unaltered. So Z, R. Now if we evaluate this new determinant, you will see that its value is same as that of the value of this original determinant, right? So at a time we can change two rows. Here I have changed only row 1. If I wish, I can also change row 2. So at a time only two rows or two columns can be changed by using such transformations. not all the three together. You also have to keep one thing in mind, that when we are changing a row, suppose I am changing row 1, I will always begin with simplification of the elements by row 1 elements only. Like instead of putting plus sign in between the rows, I can also have a transformation like this. So row 1 changes to row 1 minus row 2, right? So, or I can also change row 2 and write row 2 changes to row 2 minus row 3. So here the new determinant that will be obtained after using these transformations, you will see its value will remain the same when compared to the value of the original determinant. So now here, as row 2 is changing, so here I begin the simplification process or calculation process by taking row 2 at first. It is not row 3 minus row 2. This will go wrong. If I am changing row 2, I have to begin with row 2. If I am changing row 1, I have to begin with row 1 only. So now let us solve some questions from the exercise to show the application of the properties that we have gone through just now. So the first question is to prove using properties. Okay. L, M, N, X, Y, Z, P, Q, R equals to Y, M, Q, X, L, P, Z, N, R. Now we'll always begin with any one particular side. Here I prefer to start from the left hand side. We will simplify the left hand side, means using properties we will simplify the left hand side and try to obtain the right hand side determinant. So here what do we observe? The elements in the left hand side determinant are same as the elements in the right hand side determinant, right? But only the position of the elements are different. So here we will think of properties which help to change the position of the elements. So two properties come to my mind right now. One property says interchanging the rows and columns of a determinant does not change the value of the determinant. So that's possible. Another property that helps to change the position of the elements is when we interchange any two adjacent rows or columns, the value of the determinant remains the same but the sign changes. Now aim at one particular element from the left hand side. Look at the element Y. Here Y is in the second row, second column. Look at the right hand side. Y is in the first row, first column. So we have to take Y from the second row to the first row, and then we have to shift Y to the first column. So let us do this stepwise. So left hand side, the determinant is L, M, N, X, Y, Z, P, Q, R. Okay. Now this Y has to be taken to row 1. So row 1 and row 2 are interchanged. So when row 1 and row 2 are interchanged, the property says I need a negative sign in front, and now we can interchange them. X, Y, Z, L, M, N, P, Q, R. Next, I wish to take Y to the first column. So, I am just drawing a line. Now, we will simplify here. Now, column 1 has to interchange with column 2. So, we are carrying forward till here. So, this gives another negative sign. We already had a negative sign and another negative sign comes now. Okay. We have now Y, M, Q, X, L, P, and the third column remains unaltered, You can see here we had a negative sign, another negative sign has come here, so minus into minus becomes plus, right? Now look at y. Y has come to the first place, that is the first row, first column, but look at the rest of the elements. The rest of the elements do not match with the right hand side positions, right? Now let me read out the first row elements that I have obtained. They are y, x, z. Where do I have y, x, z here in the required part? I have it in the first column, right? So first row should become the first column. That means I can think of the property interchanging all rows and columns of a determinant does not change the value of the determinant. So let us interchange all the rows and columns now. So the first column will become the first row. Second column becomes the second row. And the third column becomes the third row. So this is how we have obtained the right hand side, and by application of property we have proved it. I'll suggest always mention the property that you are utilizing to solve such questions in the right hand side part. Okay, here you may state all the properties that you have used. Let us move on to another question. Next question, please see this one. 1, 1 square, 2 square, 2, 2 square, 4 square, 3, 3 square, 6 square. So either evaluate or prove that this is equal to 0. Okay, so to prove that the value of this determinant is equal to 0. Now let us begin with the left hand side. So here what I can do is I can see factors of 6 are 2 and 3. So 6 can be written in terms of 2 and 3, right? 4 can be written in terms of 2. So let us try. I'm writing them as 1 square, 2 square, 3 square, and over here 1 square into 2 square, 4 square means 2 square into 2 square, 6 square means 3 square into 2 square. Now one property is already visible here, that is a common factor that is available in any one row or column can come out of the determinant sign. So look at the third column. Column 3, you can see 2 square is the common factor throughout. So 2 square can come out. And what are we left with then? The other rows remain unaltered. Other columns, I mean, remain unaltered. So here 1 square remains, 2 square remains, and 3 square remains. What do you observe now? Look at column 2 and column 3. So column 2 and column 3 are identical. So when any row or column is identical, what do we get? We get the value of the determinant as 0. So this is equal to 0, equal to right hand side. Fine, proved. Let us solve another question. So here I have shown you already application of 2 to 3 properties. Now another property. So let us begin with the left hand side here. Now if you look at the left hand side, you can see that each of the terms or each of the elements here are expressed as the sum of 2 terms. Now we cannot split up this determinant in terms of 2 determinants by splitting each of the elements, right? So we have to first of all look into the right hand side. We need 2 as one of the common factors, right? So which transformation should we use so that we get a factor as 2? Now see here, if I change column 1 elements as column 1 changes to column 1 plus column 2 plus column 3. So when I am changing column 1, remember we have to add sidewise, means this column added to this column and this column. We have to add sidewise. When I talk of row transformation, then we will either move downwards by simplifying the elements of the rows, or we have to move upward from third row to the upper row. So we can either move up and down when we are using row transformations, but if we move sidewise, that means we are using column transformation. Now column 1 elements will change. How? By adding column 1 elements to column 2 and column 3 elements. So the first element should be added to the first elements only. So B plus C plus C plus A plus B, right? So I get twice of A plus B plus C. All the column 1 elements will change. Similarly, if I add Q plus R with R plus P and P plus Q, I will get twice of P plus Q plus R. Next, Y plus Z added with Z plus X and X plus Y. That also will give me twice of X plus Y plus Z. So here column 1 elements have changed. The remaining columns I do not change right now. So I will leave the other columns unaltered. Now one more property is applicable. If you see, 2 is a common factor in the first column. So 2 can come out. And we are left with A plus B plus C here, P plus Q plus R here, and X plus Y plus Z. And the remaining elements to be written as they are. Z plus X, A plus B, P plus Q, X plus Y. Let me rub the upper part of the board. Now I shall use another property, the property that I used in the very first step. Now I will try to subtract elements. So from here, see A plus B plus C. If I remove C and A, I will be left with B. So if I subtract sidewise, so column 1 and column 2 when subtracted can give me a single element in column 1. So column 1 changes to column 1 minus column 2. So this gives me A plus B plus C minus A. I will be left with B. You can work out in the rough column and check what remains. So P plus Q plus R minus P. So Q remains. And X plus Y plus Z minus X. Y remains. Right. Next, the remaining elements remains the same. I am not changing them right now. Okay. A plus B, P plus Q, X plus Y. Now in the next step, again I will be using the same property. Now I will aim at keeping a single element either in the second row or either in the second column or the third column, whichever is possible. Now here I can see if A plus B is subtracted by B, I will be left with only A. Similarly, P plus Q minus Q can give me single element P. So column 3 now changes to column 3 minus column 1. Right. So this gives me, other columns will remain unaltered. Let me copy them as they are. So R plus P, Z plus X. Now A plus B minus B gives me A. This will give me P and X. Now we are left with the middle row. That is the we are left with the second column. So I am rubbing the lower part of the board. So now another transformation here. If the second column is subtracted by the third column, you can see we will be left with a single element. C plus A minus A will give me only C. So row 2 changes to row 2 minus, sorry, column 2 changes to column 2 minus column 1. So this gives, other elements remain unaltered, right? So I am copying them, and now I will use the transformation. So C plus A minus A gives me C. R plus P minus P is R. Z plus X minus X is Z. So we have got single elements in each of the positions, but our requirement is not yet fulfilled. You can see we have B in the second column and A in the first column. So now we have to interchange two columns. So let us take B to the second column, or in fact if I bring, so now let us take A to the first column step by step. First of all it will go to the second column, then it will go to the first column. So column 2 and column 3 interchanges. Do not forget a negative sign has to come. Okay, so B, Q, Y, A, P, X, C, R, Z. So third column is the necessary part of the answer. Next, column 2 has to interchange with column 1. So another minus sign comes here. So we have A, P, X, right? Then B, Q, Y, C, R, Z. So minus into minus is plus. So twice of A, B, C row wise, P, Q, R, X, Y, Z. So you can see this is the right hand side, hence proved. So this much for today. In my next video I shall come up with more problems. I'll show you how to use the properties to solve more questions. Thank you. Good day.